Okay, so last time we've obviously talked about bonding a great deal. Um, so we talked about hybridization, we talked about molecular polarity. There's really only one sort of section of sort of bonding still to go, and we're actually not going to, excuse me, we're not going to actually cover it. So we are going to skip molecular orbital theory. So you will not be responsible for molecular orbital theory. You'll just be responsible for, in terms of bonding, what we talked about up until yesterday. And I think that should be sufficient. So there's probably another little section or topic there in the bonding chapter, which is known as again molecular orbital theory or MO, and we're not going to actually discuss that this time around, I think. So what that means is we're pretty much sort of done with the bonding aspect of it. We are going to kind of change gears right now, and we're going to go to chapter 5. Like I mentioned before, we will go back to chapter 3, which is where we were, I think, after this chapter, and we will pick up the last little bit of nomenclature. We'll talk about naming and all that kind of stuff. So we're going to, again, like I said, kind of switch gears here, go to chapter 5. We're going to talk about grams. We're going to talk about moles, Avogadros number. We're going to talk now about sort of empirical formulas, molecular formulas, and how to calculate those and sort of determine those as well. So a little bit more calculations now in this chapter. All right, so let us get started here. Get a couple of things out of the way. All right. Okay. So really, the first thing we're going to kind of talk about is in this sort of grams, moles, is atomic mass. And atomic mass, as you may remember from a little earlier conversation, probably around when we were talking about atomic number and mass number and stuff like that, the atomic mass is basically the mass of an atom based on obviously the protons, electrons, and neutrons that are present. Um, it is, as we talked about when we were talking about probably mass number, as with the idea that mass number is not found on the periodic table, but atomic mass is found on the periodic table. So if you go to periodic table, that number that is underneath the symbol there is the atomic mass. And basically, what that means is if we kind of grab off that number there, it will tell us really the mass of it per atom. So, for example, hydrogen means that that is 1.008 AMU is one atom of hydrogen. AMU, as we will see, is sort of a unit of atomic mass. Is atomic mass unit is what that stands for. Atomic mass unit, AMU. So when we look at the periodic table, we can see all these atomic masses, obviously, for every element, all has numbers, obviously, underneath there. As we talked about earlier, again, that is not the mass number. So, again, that is something different when we talk about the mass number. So, obviously, it is the mass of the atom, and atoms are extremely small. So, you can't really, kind of pick up an atom and put it on a balance or anything like that, which is a scale, and weigh it. So oftentimes, in science and especially in chemistry, when there's kind of no way to perhaps directly measure something, we oftentimes will sort of choose something as a standard and choose something as a standard to sort of compare everybody else to. And they did that for atomic masses, and sort of the standard that they chose to use to sort of compare everybody else to use to try to figure out what the atomic mass of everybody is was an isotope of carbon. And they basically used a carbon 12 isotope. So they used this carbon 12 isotope. isotope as basically the standard to be used basically to compare everybody to. Carbon 12 basically has 6 protons, it has 6 neutrons, and it has a mass that was basically decided to be exactly 12.00 AMU. Again, an AMU, as I mentioned, is an atomic mass unit. It is also sometimes referred to as a Dalton, and stuff like that. I will say we don't use it too much, atomic mass units. We do and we don't. We don't necessarily use the unit of atomic mass units. As we'll see a little bit later in this chapter, we kind of use grams per mole, which, as we will see, is equivalent to basically atomic mass units. So one atomic mass unit is basically 1/12 the mass of a carbon 12 isotope. And again, 1 AMU is basically sort of that conversion. So how did they sort of come about, getting sort of the masses of all the atoms if you can't really weigh it? Well, what they basically did is they did some experiments, and they basically said, well, hydrogen is only about 8% as big as a carbon 12 isotope. So they did some type of math to basically figure out, okay, what is 8% of 12? Because 12 is our standard, and if hydrogen is only about 8% or so as big as carbon 12, then we can kind of do a little math there and make obviously we'll say guess, but a calculation as to what the mass of hydrogen is. And that's essentially what they did, is that sort of process. The atomic mass, for example, again, of hydrogen, it was found that it again is about 8.4% as massive as a carbon 12 isotope. And again, what they basically did is just a little math problem here. This is basically 8.4% times 12, right? 8.4, if you want, divided by 100, gets you 0.084, or move the decimal 2 places over. But basically that's 8.4% times, again, the atomic mass of our standard isotope, which is 12, gives us a value of 1.008 AMU. And again, if we look, just as we just saw there a second ago on the periodic table, that is the number that we do see underneath hydrogen there on the periodic table. Now, similar calculations were done to basically figure out pretty much the atomic mass of everybody that we see on the periodic table under there. And again, basically that number can be taken off the periodic table as how many AMU there are in one atom of that particular guy. In addition, something with atomic mass, and typically speaking later when we talk about molar mass, when we do go to the periodic table, we do pull off pretty much 4 significant figures is typically what we take off of the periodic table. So for example, here we have the 1.008. On some periodic tables, it may not be rounded to that. It may be obviously something very different, like 1.00794. It's a whole bunch of numbers. So depending on your periodic table, you may have a significant amount of numbers for the atomic mass. For example, one I might be looking at right now has about 6 numbers for every atomic mass. And again, typically speaking, we do round when we take it off the periodic table to about 4 significant figures. And that's a good practice to do, again, for atomic mass. Also, later on when you kind of use it for molar mass, 4 significant figures is usually a pretty good one. Thus, we get something like 16 AMU for oxygen, 55.85 for iron. And again, on the periodic table, we can find pretty much the atomic masses listed for every element. Now, an interesting thing that you may be thinking to yourself is, well, when I look at carbon, for example, on the periodic table, I see a number of 12.011, for example. And you may be saying to yourself, wait, carbon was the standard and it had a mass of 12.00 AMU. What sort of gives here? And there is a reason for that. And there's a reason really why it's not 12. And it has to do with really the reason where all the numbers sort of come from. What we actually sort of see on the periodic table is really the average atomic mass, although most people never call it the average atomic mass, they just call it the atomic mass. But it really is an average atomic mass. And what is it an average atomic mass of? It's really an average atomic mass of all the naturally occurring isotopes for that particular element. So, for example, carbon has a couple of isotopes that naturally occur, carbon 12, carbon 13. And the value that we see there for carbon of 12.01 is really the average value of those naturally occurring isotopes. So it's really the average between the mass of the carbon 12 isotope, the average from the mass of the carbon 13 isotope. So really all the numbers that we see on the periodic table are those average sort of values of all the naturally occurring isotopes. Some have two, some have three naturally occurring, some maybe even only have one. But it's sort of an average value for each of those. Again, most people don't call it an average value. They just basically call it, the atomic mass. So how do we calculate sort of like a value that we see on the periodic table or the atomic mass? Well, we take a kind of a general formula like what I'm going to write here, and we use it to calculate the atomic mass. The atomic mass is basically equal to the percent abundance of one isotope times the atomic mass of the first isotope plus the percentage of the next isotope times the atomic mass of the second isotope plus you just kind of keep following that pattern. So let's talk a little bit about what these things are. So when we do have isotopes that occur, they don't necessarily occur in the same percentage. So for example, when we talk about maybe carbon 12 or carbon 13, maybe carbon 12 occurs about 99% of the time, and maybe carbon 13 occurs about 1% of the time. And that allows us to figure out the percent abundance. And that's basically what that is, sort of the percentage. So when we talk about all the naturally occurring isotopes, that should equal 100%, right? So again, for example, if one occurs about 99% of the time, one occurs about 1% of the time, that's 100% of all the naturally occurring isotopes. And that's what is referred to as the percent abundance. Now, the percent abundance, you do need to write when we do anything that involves sort of percentage in a calculation, we do need to make sure that we do convert it into like a decimal. So you either need to divide the percentage by 100 or just move the decimal point 2 places left, kind of like what we did with the 8.4%. And you can multiply it by the atomic mass of each of those isotopes. The key here in sort of this formula is this part here. Most of the time people want to multiply these things, but you are adding. So you're basically taking the percentage of how often the first isotope occurs times the mass of the first isotope. Then you're going to add it to the percentage of how often the second isotope occurs times the mass of the second isotope, and so forth. So if we take a look at, like I mentioned before, carbon here, again, as I mentioned, there's basically two isotopes of carbons, carbon 12 and carbon 13. And we see that carbon 13 occurs about 99% of the time, 98.89% of the time. And the carbon 13 isotope occurs 1.11% of the time. So these are the percent abundances that are a lot of times given to you, or the relative abundance is sometimes referred to. Now, we know the mass of carbon 12, as we talked about, is 12 AMU. The mass of carbon 13 is about 13.00335 AMU. So we basically can use our formula that we just saw there. So this is the 98.89% converted into a decimal, right? So that's our 98.89%. And we're timesing it by the mass of the carbon 12 isotope here, which is 12. Again, we're going to add it to the percent abundance there of our carbon 13 isotope, which is basically 1.11%, again, converted into a decimal, times the mass of our carbon 13 isotope. And we're going to add them together. And that is where the 12.01 comes from when we look on the periodic table for the atomic mass of carbon. And again, that is why carbon does not say 12 like you might expect it to be, since it was chosen as the standard. Why it says 12.01 here, as it's the average atomic mass of all the naturally occurring isotopes for that particular one. Question sort of on that calculation there. We're going to talk about in a little bit here in this chapter sort of how you get those sort of percentages and some experiment that you can kind of run to sort of figure those things out. It is important to remember that we do sort of consider the atomic mass of something like carbon as 12.01. It is really an average atomic mass. And in reality that, you know, if you were to grab up some carbon sort of atoms or isotopes, you really would never find one that has a mass of 12.01. You would either find one that has a mass of carbon 12, which is 12, or you'd find one that has a mass of carbon 13, which is 13 and some change. But you'll never really find one that is 12.01 again, although that is sort of the value that we use for it. There really isn't one. It's just, again, an average value of all those naturally occurring sort of isotopes that occur. Now, atoms are obviously very tiny, so to avoid using small numbers, we do use these sort of AMU. So an AMU is equal to 1.66 times 10 to the minus 24 grams, and that obviously is a very, very small number. So that's sort of a conversion factor. You could go between AMU and grams. The average atomic mass for an element is a weighted average, as we just did there, of all of the naturally occurring isotopes for that particular element. That's also why when we think about molar mass, which we'll talk about a little bit later on, you know, we do something like hydrogen is 1.008 grams per mole. We do sort of a conversion and stuff like that, and some unit conversions to allow us to sort of use, let's say, regular numbers. Like if you look at all the numbers we see on the periodic table, they're kind of like, you know, normal numbers, whole numbers and stuff like that. They're not like to the minus 29 or something like that, sort of grams and stuff like that. So as I mentioned before, and as we just saw there again, even though naturally carbon does not contain an atom with 12.01, we do use that number basically as sort of our mass of carbon, and it enables us basically to sort of weigh these guys. We can use AMU in some calculations from the periodic table, and I'll be honest with you, you know, we probably don't use it all that much in calculations in terms of AMU, but it's a good thing to sort of realize, and you know that you could kind of do it as a conversion factor. So if we did want to calculate the AMU of, or the mass in AMU of 431 atoms of carbon, we would go to the periodic table. And again, as I mentioned before, we can sort of use that number on the bottom there as how many AMU there are in a carbon atom. There's basically 12.01 AMU, as it says there, in one carbon atom. It really does give us two conversion factors. We could do 12.01 AMU per atom. We could also flip it around, put the atom up on top, per 12.01 AMU. Here we are starting with carbon atoms. So we would use the conversion factor here on the left, which is what they did. Atoms will cancel, gives us 5,176 AMU in terms of our answer. Same thing here with aluminum. Again, if we look at aluminum on the periodic table, 2698 is what we see sort of underneath there. Again, meaning that there is 26.98 AMU in one aluminum atom, giving us two conversion factors of 2698 AMU per atom. R an atom is 26.98 AMU. Here again, we're starting with atoms, so we'll use our guy on the right there. That's going to allow our atoms to cancel, leaves us with AMU, and we end up with 2024. So really, you can use this again to figure out the mass of these guys in AMU. As I said, probably as we'll get going here, grams per mole, which is something you're probably familiar with, is more so sort of the units that we'll use. As we will see, grams per mole and AMU per atom is essentially the same number. So it actually comes out the same numbers and stuff like that. But again, that's sort of another definition that you can get from basically the periodic table there. Any questions on that there? So a second ago, I mentioned that, how do we maybe figure out, the mass of these different isotopes? How do we figure out sort of the relative abundance or percent abundance? And we can use a process which is known as mass spec or mass spectrometry. It's basically a process where the masses of isotopes and their relative abundance really can be measured through this process. Basically, atoms or molecules are ionized. They're sort of sent down a tube. Some of the molecules are put into fragments, are broken up during this ionization process. These guys are basically separated out by mass. So they come out of the graph basically at the end and are separated really by the mass. Kind of the lighter ones maybe come out first. The heavier ones come out second in terms of these isotopes. It sort of goes down this path. It's actually meant by a magnetic field, also a little electrical field involved there as well. Kind of similar to Thompson's cathode ray experiment, remember, as we talked about, because things have charges and stuff like that, things are affected by magnetic field, electrical field as well. And what ends up happening is we get these sort of graphs like we see here on the right, and we get the relative masses of these different isotopes sort of come out. As you can see here, we're looking at chlorine 35 and chlorine 37. And we also get the relative sort of abundances that they come out at, 75-ish percent, roughly 25-ish percent. It's roughly 100%. Remember, it's experimental, so it may not be 100% on the nose, but should be fairly close. And we get the relative sort of masses of each of these isotopes and their basically abundance to which they come about through this sort of process here. And here's sort of a picture of what a mass spec looks like. Again, you basically send it sample through here. It gets ionized here, basically heated up and vaporized. It goes through, again, an electrical field and then also goes through a magnetic field. Each of these are really going to kind of separate them out by charges and so forth as they sort of gain charges as they get separated. And as they come out to the sort of the detector field, they do get separated out by kind of mass, if you will. Kind of the lightest guys are over here. The heavier guys are over here on this side. And again, on the graph, as we just saw, they then kind of are separated out, by mass, and they have different, obviously, abundances that basically occur. So this is sort of how we get to those sort of what we saw previously there with carbon. The carbon 12 isotopes like 99%, the other guy is about 1%. This is how we could kind of do that and also get the relative masses of these guys by using a technique such as this. So why don't you give one a go here and see what you come up with. If copper is 69.17%, copper 63 with a mass of 62.9396 AMU, and the rest is copper 65 with a mass of 64.9278. Find the atomic mass in AMU of copper. So why don't you take a few minutes and see what you come up with. Okay, let's take a look at this. So again here, we're giving a couple of isotopes here of copper. We have copper, maybe, there we go, copper 63. And for copper 63, we know it occurs 69.17% of the time and has a mass of 62.9396 AMU. The other one we're looking at is copper 65, which has a mass of 64.9278 AMU. And we're looking for the atomic mass of copper here. So we can use, again, our formula that we saw before, that the atomic mass is basically equal to the percent abundance times the atomic mass of the first isotope plus the percent abundance of the next isotope times the atomic mass of the second isotope, and so forth. In this case, we actually only have two isotopes. We are sort of missing this guy's percentage here. So if we make a pretty common assumption and probably a safe assumption that both of these guys are all the naturally occurring isotopes for carbon for copper, that means that really their percentage should add up to 100%, right? If they're basically all the naturally occurring isotopes, that should give us 100% of the abundance that's present. So we can find sort of the missing percentage of copper 65 by simply taking 100% minus the 69.17%. And that will give us, or should give us, really the percentage of copper 65 that there is. And if we do that, it looks like we end up with 30.83, I think, 30.83. And that gives us our sort of missing percentage there. So again, in this situation, it is pretty safe to assume, if they sort of only mention these two isotopes, that they are all the naturally occurring isotopes. And obviously that allows you to use sort of 100% to figure out the missing percentage there. Any questions on that there? At this point, we now have really everything we need for each of the isotopes. We have the relative abundance, we have the atomic mass. So we can go into this formula here, and we would see that the atomic mass is equal to our percent abundance. So remember that we do need to convert it into a decimal. So you could either divide the percentage by 100 or just move the decimal point, which is what I'm going to do here, and go 0.6917 times the atomic mass of that first isotope. That essentially is 69% times our atomic mass. Again, it's going to be an addition here, not multiplication. We're going to do the same thing here with our second percentage. And again, just to show you your other option, you could go 30.83% divided by 100%. That's going to move your decimal place for you, and times it by 64.9278 AMU. And if we do all that good stuff there, we end up with 0.6917 times 62.9396. It's about 4354, give or take, plus basically 3083 times 64.9278. Gets us an atomic mass of 3.55 AMU. Any questions on that there? Now, if you go to the periodic table, for example, the periodic table that I can see, and it's got something maybe like 63.546. Again, rounding it to about 4 significant figures takes us to 63.55. So again, as we can see here in this particular case, that is an average value really of the copper 63 and copper 65 isotope for copper. Any questions on that calculation there? Okay, so why don't you try one here? Hang on here. Go here. Let's say we had 3 isotopes of magnesium, and magnesium had an atomic mass of 24.31 AMU. If the 3 isotopes of magnesium were magnesium 24 that had a atomic mass of 23.99 AMU and a percentage of 78.99%, magnesium 25, which had an atomic mass of 24.99 AMU and a percentage of 10, relative percentage or abundance. And if we had magnesium 26, what we want to know is what is the atomic mass of magnesium 26 in AMU. All right, so take a couple minutes to see what you come up with. We're actually looking for magnesium 26. We're looking to determine what is the atomic mass of that particular isotope. So take a few minutes, see what you come up with, and we'll talk about it. In this case, we kind of want to use perhaps the same formula that we just used. So that again would be, in this case, the atomic mass would equal the percentage of basically magnesium 24 times its atomic mass plus the percentage of magnesium 25 times its atomic mass and plus the percentage of magnesium 26 times its atomic mass. In terms of sort of what we have given to us, we do have the atomic mass of magnesium given to us. So we actually have this number given. We do have the percentage of 24 given to us and the actual mass of 24. So we have everything in there. We do have the percentage of magnesium 25 and the mass of it given to us. So we have everything in here. We are looking for really the atomic mass here of magnesium 26. So we don't have that. And we don't have this. Now, out of those two things that obviously we don't have, one thing that we can get to is actually the percentage of magnesium 26, using the assumption that these guys would be all the naturally occurring isotopes, which means when we add up their percentages, it should really equal 100%. So using the idea that 100% should equal all these guys, we could use that really to figure out the percentage of magnesium 26. And that would be obviously 100%, which should be everybody, minus we already know that 78.99% of it is the magnesium 24. And we already know that 10% of it is the magnesium 25 in that case. And if we do that subtraction, that's 100 minus 78.99 minus 10, it looks like, gives us an 11.01%, which should be, just kind of move that arrow that way, should be the percentage here of magnesium 26. So we should now know that this is 11.01%. Any questions on that move right there? That now really does give us this, and we really have just one unknown. So we could really just make it like a math problem at this point. We basically put in the numbers that we do have. So if we put in the numbers that we do have at this point, we got 24.31 AMU is the atomic mass of magnesium overall. Our percentage of magnesium 24 is 78.99%. We're going to convert that into a decimal by moving the decimal place. We're also going to multiply it by the mass of it, which is 23.99 AMU. We're then going to add it to our magnesium 25, which has a percentage of 10, which becomes 0.1000 times the atomic mass of magnesium 25, which is 24.99 AMU. Plus, we now figured out that our last isotope there, which we're looking for, is 11.01%, which is 0.1101. And that's going to be times the AMU of that isotope, which is actually what we're looking for. So in this case, I'm just going to call that X. So that's kind of like what we're going to try to solve for. X will equal the AMU of magnesium 26 in this case. All right, so doing some cleaning up here gets us 24.31 AMU is equal to 0.7899 times 23.99. Gets us about 18.95 AMU plus 0.1 times 24.99. Gives us roughly, we'll round it a little bit here, 21.45 AMU plus 0.1101x. So these two guys basically there. Now we're going to subtract that 2145 to the other side. So we're going to bring it over there and subtract it. And if we do that, 24.31 minus 21.45 gives us a 2.86 AMU. And that would equal 0.1101x. At this point, we will divide both sides by this. Obviously, that will cancel. That gives us an x of 25.98. Pretty close to 26 AMU, and that should be the atomic mass of magnesium 26 in this case. Any questions on any of those steps there? So again, this is the formula at which you can basically calculate the atomic mass of an element by using the percent abundance of each of the isotopes and their atomic masses. And obviously, as you see in these couple of examples, you can be asked to find what is the atomic mass of the element. You can be asked to find what the atomic mass of a particular isotope is. Or you can even be asked to find the percent abundance of everybody. The 2.86 came from subtracting. So the question is, where did the 2.86 come from? It came from, we basically moved the 21.45 to the other side and subtracted it. So 24.31 minus 21.45, 2.86. Again, by bringing this guy to the other side. Other questions? You can wait to the end. You could wait to the very end for rounding. I think I did round here, to 4. It should come out. It should come out similar. You might get a slightly different answer at the end if you didn't round maybe in this region. It would still be okay. In this case, I did go to 4 because I was dealing with really 4 sig figs on both of these. So I decided just to round it at that point. But if you didn't and you got a slightly different answer here, it would be okay still, I think, if you just waited to the end to round. Other questions? Okay, so again, this is obviously how we would calculate atomic mass. Again, it's really how those values that we see on the periodic table really do come from And again, you may be asked to obviously solve for any of those things, like I talked about, overall atomic mass, a percentage of an isotope, or even an atomic mass of an isotope like we did here. Okay, so the next thing we're going to talk about is everybody's favorite, I think, maybe. It is moles and Avogadro's number. So in life, we do have a lot of words that, do represent a certain meaning. So like we see here, if we say we have a dozen eggs or a dozen cookies or whatever it may be, when somebody says we have a dozen of something, that sort of name does represent a specific amount, and obviously it represents 12 in that particular case. Just like if we had a pair of shoes or a pair of something else, I don't know. And basically a pair means two when we sort of say that word pair. And in chemistry, we also have a word that does represent a certain amount of something, and that word is mole, not the furry guy, but the mole here. And by the way, that is the abbreviation for mole. I had to cut off something, so they cut off the E. So when you do see MOL, it is the abbreviation for mole. It is not the abbreviation for molecules, which sometimes people sort of get those guys confused. But mole basically represents the amount of elementary substances there are in exactly 12 grams of our carbon-12 sort of standard isotope. And a mole does represent a certain amount. It represents basically what is known as Avogadro's number, and that's what's on the bottom here. Basically, we can say that 1 mole of anything basically equals 6.022 times 10 to the 23. This again is what is referred to as Avogadro number. And when we use like sort of Avogadro's number, there is differences in terms of the units that we can use here. So there's a wide variety of units that we could use. It really could be pretty much anything. This could be atoms, which is a very common sort of unit. It could be molecules if we're dealing with molecules. It could be particles. Could be shoes. Could be pizzas, Could really be any type of unit that you want. I would say probably here in chemistry, not too many shoes or pizzas, but it technically could be. But we use atoms a lot with Avogadro's numbers. We use the units of molecules a lot with Avogadro's number. And then we do round Avogadro's number usually to that. So 6.022 times 10 to the 23. We basically use Avogadro's number as sort of a conversion factor to go between those sort of units there. We use it really to go between moles and atoms, or moles and molecules, are backwards if you start with atoms or if you start with molecules to get to moles. So it's sort of our conversion factor to do that, basically to go from moles to atoms or molecules, which are the two common ones we use it for, are backwards. And again, Avogadro's numbers is used to do that. We basically can write two conversion factors for using Avogadro's number. We could say, for example, if we're talking about hydrogen, so we could say in 1 mole of hydrogen, there is 6.022 times 10 to the 23 atoms of hydrogen. Here we would use atoms because we're talking about just an atom of hydrogen. And we can write two conversion factors. 1 mole of hydrogen is 6.022 times 10 to the 23 atoms. Or we could put Avogadro's number up on top, is 1 mole of hydrogen. We could do that for really any element. We could say 1 mole of copper would have 6.022 times 10 to the 23 atoms of copper. And again, also can write two conversion factors for this guy, just like above. are putting Avogadro's number up on top. Now we use atoms here because, in this case, we're talking about a hydrogen atom or a copper atom and so forth. We could also apply Avogadro's number to things that are not atoms, but things that are molecules. So we could definitely say, for example, in 1 mole of water, there would be 6.022 times 10 to the 23. These would be molecules of water, which also would lead us to 2 conversion factors. We could write 6.022 times 10 to the 23 molecules over 1 mole of water, H2O, or again, on the opposite way, 1 mole of H2O is 6.022 times 10 to the 23 molecules of water. Here we use molecules instead of atoms as a unit because water is a molecule. It's not just an atom. And again, you could do that for anything, 1 mole of CH4, also a molecule, would be 6.022 times 10 to the 23 molecules. So again, we use Avogadro's number really as that conversion factor, as I mentioned, to go between, atoms and molecules and moles. Now, it's important to remember that, sometimes people go, I know Avogadro's number, I should probably use it in like every calculation I ever do. And you definitely don't want to use it in every calculation that you do. You really only want to use it when either 1 or 2 situations basically occur. One situation is obviously you're given a number in the problem, for example, in atoms or molecules or something like that, and you would obviously use it to convert to moles. Or you're asked to solve for something in molecules, atoms, or something of that nature. If there really is no sort of mention of atoms, molecules, particles, any of those things, you really shouldn't be using Avogadro's number. So again, sometimes people want to kind of use it in every calculation because it's like it's a number. I'm supposed to like use it, but you don't necessarily need to use it in every single calculation. So it's an important distinction to make sure that if you do use it, you are using it sort of in the right way. Another really important aspect of sort of mass and all that kind of stuff that we're talking about is what is referred to as molar mass. Now, molar mass is taken from the periodic table as well. It is also the number that we see on the bottom where we just talked about atomic mass. So again, here, it is this guy right here is the molar mass. Now you may be saying, wait, wasn't that the atomic mass? And it is the atomic mass, but it's also what is referred to as the molar mass as well. Here's a bunch of sort of conversions, but essentially what I was saying earlier is when we take something off the periodic table and basically AMU per atom, it is the equivalence of molar mass, which is grams per mole. The actual number is pretty much the same. It doesn't change. So molar mass is typically the units of molar mass are grams per mole. The number stays with the grams part and it is per 1 mole. And molar mass is really the conversion factor for the most part that we use to go from grams to moles, which is a very, very common conversion here in chemistry. Our opposite of that, if we are starting with moles and want grams, we use the molar mass as really our conversion factor to do that. So we can go off the periodic table here for hydrogen. We could say in hydrogen, there's 1.008 grams of hydrogen in every mole of hydrogen, which gives us a molar mass of hydrogen of 1.008 grams per mole. Again, we can use it really as a conversion factor as well. We could put the grams up on top. Or again, we could put the moles up on top and do some dimensional analysis and really kind of use it as a conversion factor. Same thing if we looked up there, For our sodium says something like 2299, and that means that in sodium there is 22.99 grams per mole of sodium. And it's always 1 mole when you do molar mass. It means the molar mass is 22.99 grams per mole for sodium. Again, you could do 2 conversion factors, 22.99 grams per mole, or a mole is 22.99 grams. We could also do this for, just like we did sort of Avogadro's number, we could do molar mass for things that are just not atoms, but are molecules as well. So for example, if we did water as we did before, water is basically H2O. So as we talked about, basically you would go and find hydrogen, which is 1.008. You would find oxygen, which is 16 basically. And to get the molar mass of something like water, we basically add up all the components as we talked about before. That would give us 2 times 1.008 grams per mole plus basically 1 times 16 grams per mole. And if we add all that together, that obviously gives us 18.02 grams per mole as the molar mass here of water. Again, number stays with the grams part, always per 1 mole when you do molar mass. Again, if we wanted to, we could use that molar mass as a conversion factor, as basically fractions, 18.02 grams of water per mole. Or again, we could flip it the other way around. A mole is 18.02 grams. So again, we can use it as a conversion factor, which is essentially oftentimes what we are doing when we do a calculation like that. We are doing basically a sort of conversion factor. Now we could tie all those things together. Basically, 1 mole of carbon equals Avogadro's number, which equals 12 grams for carbon 12. So, if we said we had 1 mole of water, that would equal 6.022 times 10 to the 23 molecules of water, which would equal, as we see here, 18.02 grams of water. So again, all those things are sort of related to each other, just like what we could see here. If we had 1 mole of hydrogen, that would equal 6.022 times 10 to the 23 atoms of hydrogen, which would have a mass of 1.008 grams of hydrogen. So, all those things are sort of tied together. And again, we use them as sort of conversion factors, basically to go from moles to grams, grams to moles. That's our molar mass as a conversion factor. And again, as we talked about a second ago, going from atoms or molecules to moles, that is where we should use Avogadro's number. Now, you may not need to use kind of both of them together in a calculation, or you may need to use both of them together in a calculation. But they are basically our conversion factors. Just like I talked about earlier, when we do pull anything really from the periodic table in terms of molar mass or atomic mass, however you want to kind of word it, or whatever you may be doing, again, that sort of 4 significant figures is typically where we do round our numbers to when we're dealing with that. Any questions on that there? And like I said before, essentially when we look at the numbers on the periodic table there, that number can be thought of, as we saw earlier today, as AMU per atom, or more commonly how we'll use it is with molar mass, which is how many grams there are per mole. And again, they're numerically equal. The atomic mass in AMU per gram, basically the same. These are all sort of 1 mole samples of different elements. And sometimes people may be surprised, if you put these things like in a, sort of a test tubes or something like that, and there's like different amounts, but they're all 1 mole, but they look like different amounts. And the reason for that is when we talk about something being like a 1 mole of something, it does really represent sort of physically different amounts in terms of, say, grams, right? Or different quantity in terms of grams. You know, if we say we have 1 mole of carbon here, that means that we have 12.01 grams. If we have 1 mole of sulfur, that means if you look at the periodic table, you're dealing with about 32.07 grams per mole. You know, if this was copper, 1 mole would represent 63.55 grams. And if this is iron, obviously 1 mole of it would be 55.85 grams. So, you know, if you see a picture, for example, and they're like, hey, this is all 1 mole quantities of these things, and they all kind of look like different amounts. The reason for that is, again, is, you know, when we say we have 1 mole of carbon, that means sort of a different amount of, in terms of grams, of what 1 mole of, you know, sodium maybe, or 1 mole of boron or something of that nature. So here's this, again, a little bit of a conversion between atoms and grams and AMU. And really using these conversion factors, we see that this is really why kind of AMU per atom is sort of the same as grams per mole. It really does come out the same in case you ever want the conversion factor between these. But again, we kind of use these values here to make the numbers a little bit more manageable than leaving them maybe, you know, just in grams by itself or AMU by itself, which would give us very, very large sort of numbers. So this is just a decision tree here on the bottom. And again, as we talked about, this is basically, you know, what we use as our conversion factors. So this is really grams and moles here. So again, it is the molar mass that allows us to go back and forth between them. This is basically moles, and atoms are molecules. And again, here is where we would use Avogadro's number as our conversion factor. Again, we don't want to use it in every situation unless, obviously, you know, it mentions something about atoms or molecules. Any questions on that there? Okay, so let's take a look at one here and see. Calculate the number of grams of iron there is here, and 15.7 moles of iron. So why don't you take a second here and see what you come up with in case you don't have a periodic table. If we looked at iron up there, it looks like 5585. All right, take a moment here and see what you come up with. Look, calculate the number of grams in 15.7 moles. So first off, I do not need to use Avogadro's number here because there's no mention of molecules, there's no mention of atoms or anything like that. It is basically, we're going from moles to grams, and that is the molar mass that allows us to do that. That is the molar mass from the periodic table. And again, when we see that number on the periodic table, that basically means that there's 55.85 grams of iron in 1 mole of iron, or the molar mass of iron is 55.85 grams per mole. Again, really can be used as a conversion factor, you know, so you could kind of set your problem up as a dimensional analysis approach. And basically, if we do it that way, we are starting with 15.7 moles. We want to get rid of moles. So we are going to use conversion factor like that. Again, setting it up so we can see all our units canceling like we should be doing. That gives us 55.85 grams. Again, the moles here cancel. We're going to take 15.7 and times it by 55.85. That gives us 876.845. The units are grams of iron. Significant figure wise, this is basically a conversion factor that we don't have to worry about sig figs. We would default back here. This guy's got 3 significant figures, which means we really should probably round it up to here. This is going to make this guy go up by 1. That means 877 grams of iron probably should be the correct answer there. Any questions on that one there? Okay. Then let's take a look at another one here with it, which is lithium. How many moles of lithium are there in 77.8 grams of lithium? Again, here, take a moment or two and see what you come up with. Lithium from the periodic table, 6.941. Okay, so same idea here. We are looking for moles. We are starting with grams. So again, no mention of atoms or molecules. So we do not need Avogadro's number here. We're going from grams to moles. So much like in the last one, it is going to be the molar mass that's going to allow us to do that. For lithium, that is 6.941 grams per mole. And that basically gives us two conversion factors, 6.941 grams over a mole, or a mole is 6.941 grams. Here we are starting with 77.8 grams of lithium. Grams are on top, so we do want to get rid of it. We're essentially dividing. We want to do that sort of dimensional analysis way here, putting our grams on the bottom and moles up on top. Again, grams here will cancel each other out. That is going to get us 77.8 divided by 6.941, going to yield us 11.2, and that would be moles of lithium here. Again, we will probably go to 3 sig figs based off of this number, as this, again, more of a conversion factor, considered kind of an exact number. So 3 sig figs there to start with, 3 sig figs there to finish with. Any questions on that one there? Okay, so I want to try one more here, another one. How many atoms are in 0.551 grams of potassium is our next one. So, oops, there we go. How many atoms are in 0.55 grams of potassium? And again, in case you don't have the periodic table, potassium looking like 3910, we'll call it. All right, see what you come up with. Okay, so let's take a look at this one. How many atoms are there in 0.551 grams? So the key word here, we see atoms. So that means we do need to use Avogadro's number in this case. So remember that is, again, 6.022 times 10 to the 23. In this case, we will use atoms per mole. Basically, per mole means that we need to get this number, which is in grams, into moles. And to do that, we do need the molar mass to do that part. So again, from the periodic table, we see that the molar mass of potassium is 39.10 grams per mole. That's going to, again, allow us to use it as a conversion factor. So the sort of pathway here, we want to take grams to moles. At that point, we then can use Avogadro's number to get to atoms. So we want to use the molar mass here. We then want to use Avogadro's number there. So if we do that, starting here with our grams, 0.551 grams of potassium. Grams are on the bottom, so we want to use the molar mass and put the grams on the bottom, which is 39.10 grams per mole of potassium. If you wanted to at this point, you could get an actual number, or you could continue on with the calculation, and that's sort of what I'm going to do here. If we just sort of follow the units at this point, if I get rid of the grams on top and the grams on the bottom, I am now left with moles that are on top. And that's important because that's going to allow us to use Avogadro's number here as a conversion factor. And if we do that, we want to get rid of moles, which means moles of potassium will go on the bottom. Avogadro's number will go up here on top in terms of atoms. That way the moles will also cancel, and that will leave us with just atoms that are left at this point. We're basically going to multiply everything up on the top and then come back and divide by what's on the bottom. And that basically means that we're going to take 0.551 times 1, basically, times 6.022 to the 23rd. We again want to make sure that we are using our exponent button when we punch that in. We want to divide it then by 39.10, and that is going to get us about 8.49 times 10 to the 21. And again, the units here would be atoms of potassium. Again, really all these guys here, sort of conversion factors. So in terms of sig phase, coming back to our original number here, which was 3, remember written scientific notation, that gives us 3 significant figures. Any questions on that calculation there? All right, let's try a few more here just to make sure. So why don't you try these two? We got to know how many moles of helium and how many grams of zinc. Okay, let's take a look at these guys here. So doing the first one there, how many moles of helium are there in 5.46 grams of helium? So again, we got mention of moles, we got mention of grams. We have no mention of atoms or molecules or anything like that. So obviously we are not going to use Avogadro's number. We're basically, again, here going from grams to moles. And again, our molar mass is our conversion factor to do that. They gave it to you here. Again, if you went to the periodic table, you would see underneath helium this number. And that basically means that the molar mass of helium is 4.003 grams per mole. We'll use that as a conversion factor here. So starting with our 5.46 grams of helium, again, grams are up on top, so opposite to get rid of it. So we're going to put the grams there on the bottom and the moles up on top. That way the grams will cancel each other out. That's going to get us 5.46 divided by 4.003. And again, going about 3 sig figs because of our original number there, 1.36 moles of helium in this case. Any questions on that one there? Same sort of approach for our one there on the bottom. We want to know how many grams there are in 0.256 moles of zinc. So again, grams and moles, no mention of molecules, atoms, or anything like that. So no need for Avogadro's number here. So if it was not provided to you, you would go to the periodic table. You would find zinc. Underneath zinc, you would see 6539. And again, what that means is the molar mass for zinc is 65.39 grams per mole. We're going to use that as our conversion factor, in this case, to go from moles to grams. Starting with our 0.256 moles of zinc, using our molar mass there, going to give us 65.39 grams per mole. Moles will cancel each other out, and looks like we will end up with 16.7, also 3 sig figs based off of this number, 16.7 grams of zinc in this case. Any questions on those two sort of calculations? Now, I'm going to talk about something here which hopefully will make sense, but in case it doesn't, then we'll talk about it again. We haven't officially talked about, equations and balancing equations and stuff like that, but I do want to mention something that's a very common mistake that people make when they go to do the molar mass of something. And especially when they're dealing with perhaps equations and stuff like that. So for example, Let's just say in an equation you had water there, and it was like 4 waters in an equation, whatever side of the arrow, right? And you needed to do a calculation that involved using the molar mass. So whenever you do the molar mass and whenever you are to calculate the molar mass, it is really based off of 1 mole, as you can see there, how many grams there are per mole. So if you happen to have something in an equation and there's a coefficient in front of it, when you go to do the molar mass, you should really always, let's say it one more time, always do it based off of just the formula, regardless of the number that's in front. So again, if we were doing a calculation where we needed to do the molar mass and it was for water, and in the equation there's a 4 in front of it, you do not incorporate the 4 into the molar mass ever. So the molar mass is strictly, you just go based on the formula, whatever it is, regardless if there happens to be a number in front of it. The only numbers you worry about are the actual subscripts that are part of the actual formula. Other than that, if there's a coefficient in a balanced equation, you do not use it. And obviously, if we were doing the molar mass of this guy, we would do it like we did earlier. It would be 2 times the mass of the hydrogen, the 2 because the 2 is part of the formula, plus basically 1 times the molar mass of oxygen, because basically that's a 1 there. And that gives us 18.02 grams per mole. And that's really the key part of it when you do molar mass, is it is per 1 mole. And 1 mole of anything is always represented basically by just the formula. So again, it's a very common mistake that people sort of make, is they incorporate that 4 like on the bottom, like 4 moles or something like that, or do something with the 4. And you shouldn't do that. We will talk about it in a later chapter, but we will incorporate that 4 when we do something like involving stoichiometry. But if you're asked what is the molar mass of it, or you need to calculate the molar mass of it, again, even if, and we won't see it so much in this chapter, I don't think, or maybe a little bit later, but if you happen to have something that is in an equation, it is a very, very common mistake when people do the molar mass. They kind of incorporate that coefficient. So the key thing to keep in mind is, if you're doing molar mass, it is based just off of the actual formula. One formula gives you basically 1 mole of it, and that's basically how you should calculate the molar mass always. Any questions on that? Okay, so we will lay it up there for today's lecture,